Today, you're not just watching another data engineering interview video. Here, you're the candidate. I'm going to ask you 5 data engineering interview questions. The questions will cover SQL, data modeling, Spark, production pipelines, and one real world incident scenario. After every question, I will give you a few seconds to think. Then I would explain how would I answer it, what the interviewer is actually testing, and how many points you should give to yourself. This interview is worth of 50 points. And the final question is the most important one because it tests something many candidates completely ignore. Can you troubleshoot a production data issue even when every job shows green? So keep track of your score, and by the end, we will find out whether the final decision is strong higher, borderline, or no higher. Let's begin. Hello everyone, welcome to Big Data Factory. I am Ranit and have 4 years of experience working as a data engineer. And if this is your first time visiting this channel, don't forget to subscribe for more content on big data and real world insights. Here are the rules. These are 5 questions. Each question is worth 10 points. When a question appears, pause the video and think through your answer before listening to mine. Do not give yourself points only because you understood my answer. Give yourself points based on what you would have answered before I explained it. Now let's start with SQL. You have a table called order status history. It contains these columns: order ID, customer ID, order status, updated date, and event ID. An order can have multiple records because its status changes over time. For example, created, paid, packed, shipped, and delivered. So here, your task is to return only the latest record for every order. There is also one additional condition. 2 events for the same order can occasionally have the same updated timestamp. How would you write this query? Pause the video and think about solution. The first thing I would identify is the partition key. We need one final row for every order. So our partition key is order ID. Next, we need to sort the records from latest to oldest. For that, we use updated date in descending order. But the question also tells us that 2 records can have the same timestamp. So ordering only by updated date is not deterministic. We need a second tie-breaking column. That is why the table includes event ID. Here is the query I would use. I use row number because I need exactly one row for every order. A common incomplete answer is take the maximum updated timestamp for every order. That gives us the latest timestamp, but it does not automatically give us the corresponding customer, status, and event columns. Another incomplete answer is ordering only by updated date. That may return inconsistent results when timestamps are equal. The tiebreaker makes the result deterministic. Give yourself 5 points if you use a window function correctly. 2 additional points if you used a deterministic tiebreaker. 2 points if you explain why a single max is not enough. And 1 point if you clearly explain the grain of the result. 1 row per order. Now we know that we can select the correct record. But querying data is only one part of data engineering. The next question checks whether you can design the table correctly before anyone writes the query. Question 2. You are designing an analytics model for an e-commerce company. The source system contains orders, order items, payments, refunds, customers, products, and marketing campaigns. The business wants to calculate daily revenue, revenue by product, revenue by customer, refund amount, payment success rate, and campaign performance. Now here the question is, how would you design the fact and dimension tables? And what is the first thing you should decide before creating any table? Pause here and think about your answer. The first thing I would decide is not the tool. It is not whether to use Spark, dbt, or Databricks. The first thing is the grain. The grain tells us what one row represents. For product level revenue, I would create a fact table such as fact order items. Its grain would be 1 row per order item. The table could contain order ID, order item ID, customer ID, product ID, campaign, order date key, quantity, unit price, discount amount, and item revenue. I would then separate dimensions such as dimension customer, dimension product, dimension campaign, and dimension date. But I would not put payments and refunds directly into the same order item grain without careful handling. Why? Because one order can have multiple items. It can also have multiple payment items, and it can have multiple refunds. If we join all of those raw records directly, we can create a many-to-many join and accidentally multiply the revenue. So I would normally model payment separately. For example, fact payments with one row per payment attempt or payment transaction, and fact refunds with one row per refund transaction or refunded item depending on the reporting requirement. Then we can create business smarts that aggregate these facts at a compatible grain. For example, Mart daily revenue, Mart product performance, Mart payment success, and Mart campaign performance. The important part is that each metric should come from a clearly defined grain. Revenue should not increase simply because we joined an order to three payment attempts. Give yourself 3 points if you started by defining the grain. 2 points if you created an order item fact table. 2 points if you separated payments and refunds based on their own grain. 2 points if you identify the risk of duplicate records. And 1 point if you included appropriate dimensions. So far, we have selected records correctly and modeled the business correctly. Now the data volume increases. The next question tests whether you understand how Spark should process that model efficiently. Question 3. You have an orders table containing around 500 gigabytes of data. You need to join it with a products table containing around 50 megabytes. The Spark job is slow, and the Spark UI shows a large shuffle during the join. Now the question is, what would you investigate and how would you optimize this job? There is also a follow-up. What changes if the product table later grows up from 50 megabytes to several gigabytes? Pause here and think about your answer. I would not begin by randomly increasing executor memory. First, I would confirm the bottleneck using the Spark UI and the physical execution plan. Then I would check how much data is being read. Are we reading unnecessary dates? Are we selecting unnecessary columns? Which join strategy is Spark using? How much shuffle is being read and written? Are some tasks much slower than others? And is there any spill to disk? Then I would reduce the input before optimizing the join. If the business needs only the last 90 days, I would filter the orders early. I would also select only the required columns from both tables. Once the input is reduced, I would evaluate the products table. If the products table is genuinely small enough to fit safely in executor memory, it may be a good candidate for a broadcast join. That allows Spark to send the small products table to the executors rather than shuffling both sides of the join. I would not broadcast it only because someone called it a dimension table. I would check its actual size and validate the execution plan. Now the follow-up, if the products table grows to several gigabytes, broadcasting it may create memory pressure or executor failures. At that point, I would allow or choose an appropriate shuffle join, confirm that join keys are distributed reasonably, and inspect for data skew. I would also verify table statistics and allow adaptive query execution to improve the plan where appropriate. The important answer is not always broadcast dimension tables. The strong answer is choose the join strategy based on actual size, distribution, cluster resources, and the execution plan. Give yourself 2 points if you started with the Spark UI or execution plan. 2 points if you filtered rows and selected columns early. 2 points if you suggested broadcasting the small table conditionally. 2 points if you explain why a larger table should not be blindly broadcast. And 2 points if you discuss its shuffle, skew, or adaptive query execution. We have handled SQL, data modeling, and Spark performance. But a fast pipeline can still produce incorrect data. The next question checks whether your pipeline is safe to rerun. Question 4. A daily orders pipeline reads file from a cloud storage and append the results to a revenue table. Yesterday's job failed after writing some of the data. The scheduler retries the job. After the retry, yesterday's revenue is doubled. Now the question is, how would you redesign the pipeline so that retries and reruns do not create duplicate data? Also explain how would you support late files and historical backfills. Pause here and design your answer. The core problem is that the pipeline is not idempotent. Idempotency means that processing the same input again should not change an already correct result. So here, I would begin by identifying stable keys. For orders, that may be order ID. For order items, it may be combination of order ID and order item ID. I would not blindly append every run. Depending on the pipeline, I would use one of these patterns. A merge based on the stable business keys, a safe overwrite of the affected date partition, or a staging and swap pattern where the result is published only after the validation succeeds. I would also track source metadata such as source file name, ingestion timestamp, batch ID, and processing status. And before writing to the final table, I would deduplicate the input using the business key and the most recent update timestamp. For incremental processing, I would use a watermark, change timestamp, source checkpoint, or a processed file tracking mechanism. But I would not treat the watermark as proof that data cannot arrive late. For late arriving files, I would support a correction window. For example, every daily run might safely reprocess the last 2 or 3 days. For larger corrections, I would make the pipeline parameterized so it can run for a selected start date and end date. The write logic must remain idempotent during the backfill. Finally, I would add validation before publication, duplicate key checks, row count comparison, revenue reconciliation, and file completeness checks. A retry should not mean append the same data again. It should mean recreate or merge the intended result safely. Give yourself 3 points if you identified idempotency as the central issue. 2 points if you used stable keys and deduplication. 2 points if you proposed merge partition overwrite or another safe write pattern. 2 points if you supported the late data and date range backfills. And 1 point if you included validation before publication. We now reach the final question. This one does not test whether you remember a function. It tests whether you can remain structured when the business is reporting a serious problem. Question 5. At 9 am, the finance team reports that today's revenue dashboard is 40% lower than expected. You check the scheduler. Every pipeline shows successful. There are no failed tasks. So the question is, how would you investigate this issue? And what would you communicate to the business while you are investigating? Pause here and structure your response. I would not start by rerunning every job. A successful rerun could make the problem worse if the issue involves duplicates, incorrect filters, or incomplete source data. I would structure the investigation in stages. First, I would confirm the impact. Is the issue affecting all revenue, or only any country, or one payment method, or one source, or one time period? That narrows the search area. And second, I would check freshness. When was the dashboard table last updated? Did the expected source file arrive? Did the source database complete its load? And did the pipeline process today's expected time window? A job can succeed while processing 0 rows or incomplete data. Third, I would compare the data across layers. Source versus bronze, bronze versus silver, and silver versus gold. At each stage, I would compare row counts, distinct order IDs, revenue totals, maximum event timestamp, null rates, and rejected records. This tells me where the numbers first diverged. Fourth, I would inspect recent changes. Was a filter changed? Or was a join changed? Did a source column got renamed? Did a payment status change? Was there a currency conversion issue? Did a new deduplication rule remove valid records? Or did an inner join unexpectedly drop unmatched records? Fifth, I would check data quality and anomaly information. Maybe the pipeline passed technically, but the revenue distribution changed abnormally. That is why status alone is not important. So here, while investigating, I would communicate clearly. I would tell the finance team, we have confirmed that the dashboard is showing lower revenue than expected. The pipeline completed, but we are validating source completeness and each transformation layer. Until the issue is isolated, please treat the current figure as provisional. I would avoid giving them unsupported cause or resolution time. Once the issue is identified, I would fix the logic or source problem, validate the correct output, safely backfill the affected period, and republish the data. Finally, I would prevent reoccurrence. That might include source arrival checks, revenue anomaly thresholds, freshness monitoring, join loss checks, schema contracts, and reconciliation between payment totals and revenue totals. The strongest part of this answer is the sequence. Confirm, localize, correct, communicate, and prevent. Give yourself 2 points if you avoided blindly rerunning everything. 2 points if you checked source arrival and freshness. 2 points if you compared each pipeline layer. 2 points if you considered business logic failures even though the jobs were green. 1 point for stakeholder communication. And 1 point for prevention after recovery. Now calculate your total. If you scored between 45 and 50, there is a strong high performance. You did not only know the tools. You explained trade-offs, production safety, and investigation structure. If you scored between 35 and 44, that is a good result. You likely have strong foundations, but one or two areas need more production depth. If you scored between 25 and 34, you understand several concepts, but your answers may still be too tool focused or incomplete. And if you scored below 25, do not take it as a failure. Use the 5 questions as a learning roadmap. SQL correctness, data model grain, Spark diagnosis, idempotent pipelines, and production incident handling. The biggest difference between an average candidate and a strong candidate is not the number of tools they mention. It is whether their answer is structured, reliable, and connected to the business problem. Comment your score out of 50 and tell me which question was the hardest. If this video helped you, drop a like and subscribe to Big Data Factory. I will see you in the next video. Till then, keep learning and keep building. Bye bye.